Hey everyone, and welcome to this explainer. Look, if you're an engineer working with embedded networks, you absolutely know this pain. You've got multiple ECUs, and they all decide to transmit data on the bus at the exact same millisecond. Usually, that means pure data chaos, a total collision. But the CAN bus, it solves this problem in a seriously brilliant way. My promise to you for this explainer is simple. By the end of it, you are going to completely master CAN bus arbitration and collision resolution. And we're going to do it using actual logic, not just rote memorization. All right, let's dive right in. Here's the game plan for today's deep dive. We'll start with avoiding network collisions, then look at the CAN broadcast principle and the actual rules of arbitration. After that, we'll walk through a real-world example with 3 CAN nodes, uncover a classic transmission gotcha, and wrap it all up with a quick summary. So, jumping straight into Section 1, avoiding network collisions. We really need to understand the fundamental problem with communication in embedded systems. Imagine a packed meeting room. What happens when literally everyone in the room starts shouting at the exact same time? Yeah, nobody understands a single word. Well, on a data bus, it's exactly the same story. When multiple nodes try to talk simultaneously, their electrical signals overlap and crash. In a lot of traditional protocols, that inevitably leads to the total destruction of those messages. And that is exactly where CAN steps up to the plate. CAN is event-driven, and it uses a method called CSMA/CR. That CR part, it stands for collision resolution. The absolutely crucial takeaway here is that CAN resolves these access conflicts non-destructively. I mean, literally zero data loss. Not a single high-priority message gets destroyed during a collision. But, how exactly does that work down on the physical layer? Well, that brings us nicely to Section 2, the CAN broadcast principle, and how bus signals interact. Let's look at how the bits actually behave on the wire. To lock this concept of dominant and recessive bits into your brain forever, let's use a really simple visual analogy. I want you to picture the CAN bus as a shared whiteboard. A dominant 0 is like a thick, black permanent marker. A recessive 1? That's a bright yellow highlighter. Now, if one node draws a 1 with that yellow highlighter, and at the exact same moment another node draws a 0 right over it with the black marker, what do you see on the board? Right, you just see the black ink. The dominant 0 completely 100% overwrites the recessive 1. Keep that whiteboard image in your head as we move to Section 3, the rules of arbitration and the math behind the CAN bus. Let's apply this marker principle to real bus logic. Taking a look at the data here, the mathematical strictness of the bus becomes super clear. If all 3 nodes send a recessive 1, so they're all using that yellow highlighter, the result on the bus is just a 1. But look at those next rows. The second that even a single node applies a 0, it pulls the voltage of the entire bus into that dominant state. This is what we call the AND logic principle. The dominant 0 always wins, completely regardless of how many other nodes are desperately trying to send a 1. Okay, let's actually put this theory into practice in Section 4. We'll look at a real-world example with 3 CAN nodes to see arbitration in action. Take a look at this CAN cluster. Node 1 has a frame with the identifier hex 56 sitting in its transmit buffer. Node 2 has hex 83, and Node 3 has hex 47. All 3 of them have data ready at the exact same moment, and they all want to transmit, so an unavoidable collision is about to happen. The question is, who wins this race? Well, remember our rule. The lowest identifier gets the highest priority. If we just compare those hexadecimal values, hex 47 is the smallest number. So node 3 powers through the arbitration phase bit by bit because it has the most dominant zeros early on in its identifier. Node 3 wins. It successfully broadcasts its frame onto the bus where nodes 1 and 2 receive it. Those other 2, they just have to sit back and wait. Now, the second node 3 finishes talking, collision resolution kicks in for the rest of the queue. We've still got node 1 with hex 56 and node 2 with hex 83 waiting to transmit. Since 56 is smaller than 83, node 1 takes the win in this second round. So node 1 sends its frame. Notice how node 2's acceptance filter immediately rejects the frame, while node 3 actually accepts it. Finally, once the bus is totally clear again, node 2 finally gets its turn to send its frame with identifier hex A3. So the sequence was processed strictly based on ID priority. And that's the absolute genius of the CAN protocol. Even though they all wanted to send at the exact same time, not a single message was destroyed. They were just neatly lined up in chronological order. But wait a second, how do the losers actually know that they lost? Well, that brings us to Section 5, the transmission gotcha. This is a super common CAN pitfall that trips up a lot of developers. If you look at the flowchart for arbitration, there is a highly critical phase called bus monitoring. You see, CAN nodes don't just blindly throw their data onto the wire and cross their fingers. Nope. While a node is transmitting a bit, it is simultaneously reading the voltage level right back off the bus via its receive pin. It's literally listening to itself speak. And here is exactly where the trap snaps shut. What happens if our node transmits a recessive one? Remember, that's our yellow highlighter. But when it reads back from the bus, it sees a dominant 0, the black marker. It instantly realizes, whoa, another node is sending a higher priority message right now. The hard rule here is stop sending immediately. In a fraction of a microsecond, that node transforms from a transmitter into a receiver and just listens to the higher priority message. And with that, we've basically cracked the core code of CAN arbitration. Let's move into Section 6 for our quick summary and wrap-up. Lock these 4 crucial takeaways into your mind. First, CSMA/CR completely prevents destructive data collisions. Second, the dominant 0 acts just like a black permanent marker. It will always override a recessive one. Third, when you're looking at the queue, the lowest identifier always wins because it has the highest priority. And fourth, this entire system only works because of active bus monitoring, where every node listens to itself and instantly backs off if it gets overwritten. And that wraps up this explainer. If this deep dive helped you get a better grip on CAN communication, definitely subscribe to our YouTube channel, Spectrum Speak. We've got a ton more survival guides on EMC and automotive communication protocols waiting for you there. Stay curious, and we'll see you in the next one.